Our system sounds a radio channel in real time and determines the location of a transmitter.
The main characteristics of the reception system is the directivity reconfiguration capacity of the antenna. But how can we implement this option into an antenna? We have one center monopole surrounded by other 4 monopoles. 3 of them will act as reflectors and the 4th one will behave as a director. The reflectors will be short-circuited with the ground reference and the director will be in open circuit with the ground. Now we need that the monopoles could change from director to reflector. For that, we will use a pin diode that works as a switch. When we feed the diode, then the monopole attached to that diode will be short-circuited and therefore will act as a reflector. We did some simulations in the CST Studio Simulator. Implementing a CPW both for power consumption and for multipath with 5 monopoles, we tried to check if an open-circuited monopole will set the directivity of the antenna. The simulations confirmed that idea. Then we tested the antenna and proved that at 5.8 GHz we obtained higher power in the open-circuited monopole than on the short-circuited. At the feeding point of the transmission line, we have 2 capacitors. This is short circuit in AC and open circuit in DC. As we move to the base of the monopole through the λ/4 length of the transmission line, the short circuit will become an open circuit, and vice versa. The diode will be located here, and when we feed it, we will short circuit the base of that monopole.
After powering up all the devices, it's necessary to program the working frequency of the PLL and the gain of the VGA. This is the structure of the front end. To test it, we will generate a PN9 BPSK signal with a single generator that will go through the LNA. IQ demodulator will be downconverted to 2 MHz by the PLL, amplified by the VGA, and sampled at 12 MHz by the ADC to be inputted into the sync array. We have repeated the test, but this time we have used our antenna array to both transmit and receive the signal. Here you have an overview of the front end.
The Silvery platform includes a Silence FPGA in the programmable logic, together with a dual-core ARM Cortex-A9 in the processing system. A hardware design is created in the programmable logic to perform the data acquisition of the incoming ADC samples. The SPI user application configures the PLL, the variable gain amplifier, and the ADC modules through the SPI interface. The second user application, called DSP, changes the directivity of the antenna and performs the direction of arrival estimation and the channel sounding of the incoming samples. It is possible to control the sync array from the laptop through UART or Ethernet, and for the final design, a simple graphical interface is created in order to plot the results in real time. A thread called RX is created and it receives samples from the programmable logic. Those samples are stored in a file for debugging purposes. From now on, the digital signal processing begins. As the carrier frequency of the incoming samples is 2 MHz, the second down conversion, the root raised cosine filtering, and the downsampling is performed. Then the average energy is calculated and stored in a file. This process will be repeated for the remainder directivities of the antenna, and the channel sounding will be applied only to that directivity that presents the highest average energy. The frame synchronization, the impulse response of the channel, and the frequency offset are calculated, and the channel sounding ends when the average energy of that directivity is lower than a specific threshold.
We tested the system for a signal coming from direction 2. The time domain waveforms show the largest amplitude for that direction. The same happens when getting the spectrum of the signal. The most powerful frequency response is obtained for direction 2.